we saw last time that any function of the type dx plus or minus omega t, where the argument of the function is linear in x and t, such that the function f is continuous and twice differentiable. That represents the general equation of a wave. General equation of transverse one-dimensional wave phenomena. Okay. And further, if the function is non-periodic, then what the wave equation represents here is a traveling pulse. Okay. So the examples were exponential pulse and hyperbolic pulse. And you have seen the formula of these functions. And secondly, if the function is periodic, then this represents a continuous or periodic wave, or you can think of it like a series of pulses which are periodic. Okay. So in that case, what happens is that the medium particles oscillate and the medium shape or the disturbance shape is also periodic. So there's a periodicity with respect to position as well as with respect to time. So if we freeze the value of time and look at the snapshot picture, there's a periodicity of y versus x. Y versus x for time being fixed. This graph is a periodic graph also. It's periodic in x. And it has what we call wavelength, lambda. Now that wavelength becomes p by k, where p is the fundamental period of the function f. Where p is the fundamental period of the original function f. Whereas if you look at y versus t, in the case of the periodic graph, look at y versus t at a fixed value of x. So looking at one particular particle's motion, you can see that this is an oscillation with a definite time period, and that time period is t divided by omega, where omega is a coefficient of time in the original function, where again t is the fundamental period. Okay. So for example, if we have the equation y is equal to e sine omega t minus kx plus some phase constant like this, then here what will happen is that the wavelength will become 2 pi by lambda. That is the periodicity of y versus 2 pi by k. That is the periodicity of y versus x. Okay. This is the cycle of y versus x for a fixed value of time. So when you look at the snapshot picture, you will see that the medium shape y versus x, that has a periodicity which is lambda. Okay. Whereas on the other hand, there is also a time period which is 2 pi by omega, and that is when you look at y versus time for a particular medium particle, it is having an SHM in this case. Okay. Similarly, for example, if we were to have the equation y is equal to 20 sine square pi by 8 x minus, let's say, 40 pi t plus pi by 6. Suppose this was the equation. Now here we want to find the amplitude, okay, wavelength, time period, Okay. Yes, that's correct. Frequency, okay, and wave velocity, that is propagation velocity. All these things. Okay. Just tell me the values of all these 5 parameters. No, you have to be a little careful, Ganesh. This is the sine square function. Notice that it is 20 sine square pi by 8x minus 40 by 2. Yes, that's correct number. Somadeep correct for amplitude. Ganesh correct for amplitude. Ganesh, your value of wavelength now is correct. Yeah, Samyak and Ayush correct. Okay, so you will notice here that it is a function of the type some constant into sine square of kx minus omega t plus 1. So sine square function has a fundamental period of p equal to pi, and also sine square function varies between 0 and 1. Okay. So you can see that y varies between 0 and e, or y varies between, in this case, 0 and whatever that 20 is. Suppose y is in millimeters in number, x is suppose in meters, and t is in seconds. Okay. So 20 millimeters. So in this case, you will see that the amplitude is actually 10 millimeters, because twice of the amplitude is from minimum to maximum. So the concept we'll understand over here is that the amplitude is equal to maximum minus minimum divided by 2. Because if you look at the snapshot picture of y versus x at any particular time, we a graph like this varies between 20 and 0. So the mean position will in fact be 10. This will be the mean position. And 20 and 0, they are the extreme positions. That is why the amplitude here is this one. Okay. Now further, you can see that the sine square function, it has a periodicity such that this thing, if it is some k lambda, that k lambda will be equal to pi. Okay. So because the sine square function has a fundamental period of pi, so my k was equal to pi by 8. So that will become over here pi by lambda, because the fundamental period is pi. So my wavelength here, lambda, will be equal to 8 meters. You can also understand by plotting the graph. And also omega was equal to 40 pi. So that is going to be pi upon time period, because again the fundamental period is pi. So my time period is 1/40th of a second, or you can write that as 25 milliseconds. And my frequency is therefore 40 hertz. Okay, people, so understood this thing. So because it is a sine square function. So for example, if you were to plot this function, if you were to plot 20 sine square pi by 8x minus 40 pi t plus pi by 3 will be 9. pi by 3 था कि pi by 6? Pi by 6. So suppose I was to plot this. For example, I want to draw the snapshot at t equal to 0. So what it would look like? Y at t equal to 0 would be 20 sine square pi by 8x minus pi by 6. So what we would see here is that this graph x in meters. Now this graph would look like what? At x equal to 0, it's sine square pi by 6. So that is 1/4. We're going from 5 to, let's say, 20. It's wearing something like this. You would see at 0, the value would be 5. At x equal to 0, the value of this would be 20 into sine square 30. Whereas it would hit the peak value of 20 at the first point where this becomes pi by 2. So that would be where? That would be where this quantity is pi by 2 plus pi by 6. Okay. So that is 90 plus 30, 120. Okay. So that should be pi by 3. So this would be the point where this is 8 by 3. Okay. Then this would be the next point, which would become where this whole thing becomes 3 pi by 2. Okay. So 270 minus 30. This point should be where it should be 240. Okay. This term should be 240. So that is 2 pi by 3. So x should become this should be 300. So it should be 5 pi by 6. So if this should be 5 pi by 6, x should become 20 by 3. You can see here that your lambda is becoming how much? Your lambda is becoming 20 by 3 minus by 3. That is, it should be 8, not be 4. Just a second. Let me calculate this x1 and x2 again. So let's say this point here is x1 and this point here is x2. So pi by 8 x1 minus pi by 6 would be equal to pi by 2. Okay, 16 by 6. So pi by 8 x1 should be pi by 3. X1 should be 8 by 3. And then this appears to be okay. And the other one is pi by 8 x2 minus pi by 6 would be 3 pi by 2. So pi by 8 2 pi by 2. Oh, sorry, yeah. So it is 16 by. This is 16 by 3. And this is becoming 5 pi by 6. So this is 20 pi by just a minute. Something is going wrong with my calculation here. This one is okay. So this is 16 by 3. So I'll just change this value here to 16 by 3. But what about this second value? x2 over here. तो यहाँ पे क्या होना चाहिए? 5 by 8 x2 minus 5 by 6 should become 3 pi by 2. So 5 by 8 x2 should become so it should become 5 pi by 6. 5 pi by 3. That's the mistake. Not 5 pi by 6, it is 5 pi by 8. So x2 should become 40 by 3. Back here, you can see that x2 is 40 by 3. So lambda is in this case as expected. Similarly, if you were to look at the relation of, if you were to look at y versus t at some value of x. So this is the oscillation of the particle at x equal to 0. So that would be how much? That would be 20 sine square minus of 40 pi t plus minus 5 by 6. Okay. So you can see that this is an oscillation again which would have that kind of relation. Like this. And again, if you were to calculate this time t1 and this time t2 and calculate the time period from this, you would see that that time period would come out to be 1 by 40 or 25 milliseconds. Okay. I'm not doing the full calculation, but you can see I've done this kind of thing in SH. Or another way to understand is that you can use trigonometry. If y is e sine square 40 pi e minus 5 by 6. इसको ऐसा भी लिख सकता हूँ because the sine square, so I can flip the signs. It can also be written as sine square can be written as what? Sine square theta can be written as cos theta can be written as 1 minus 2 sine square theta. This can be written as 1 minus cos 2 theta by 2. It can be written as a by 2 into 1 minus cos of double of this. So that will become 80 pi t minus 5. So you can also understand this in this. So this you can see y is varying between 0 and e. So amplitude is becoming e by 2. And now you can see that the omega, which is 2 pi upon time period, or the standard cos function, which you can convert to sine function, is e pi. So again, you can see that time period is 1 pi. So that's another way to interpret this. You can always convert the sine square using the cos double angle formula. So this is of the general type. Y is equal to some constant, let's say b, plus some amplitude, let's say a prime, into sine omega t plus pi. This becomes that kind of SHM where the mean position is no longer at 0. The mean position is at b. Okay. This kind of SHM is where the mean position is at y equal to b, and the amplitude is equal to e prime. Okay, so that is about all these parameters: amplitude, frequency. Okay, Sudhir, I'll explain. It's like this: कि अगर मैं ऐसा SHM लिखूं that y is equal to something, let us say 20 sine square 40 pi t minus pi by 6. This one here. Now we can write this sine square theta as 1 minus cos 2 theta by 2. So therefore, we can write y as 20 into 1 minus cos of, that will become double of this whole thing. Become 2 times this whole thing. So 45 t minus pi by 6. Whole thing divided by 2. So that will now become what? Y is equal to 10 into 1 minus cos 80 pi t minus pi by 2. So now the whole thing is about plotting this graph. This graph. So how do we plot this graph? We start by plotting y is equal to 10 cos 80 pi t minus pi by 2. We know how to plot this graph. This graph will look like something like this. I mean, here the phase, initial phase will not be. Initial value will be cos of minus pi by 3. So that is cos pi by 3, which is half. Or like this. From there it will be. But anyway, this will be varying between 10 and minus 2. So from that we know how the graph of y of minus 10 cos same thing omega t plus pi looks like. Okay, if this one is like this, then the minus 1 will become just invert this. So it will become like a mirror image of this. Okay. So the minus 1 will look like this. This is how this graph. And then we have to do what? To get this, we have to add 10 to this. So when you add 10 to this, how this graph will look like? Now you have this graph of 10 minus 10 cos omega t plus pi. Omega is t pi and pi is minus pi by. So this whole graph has to be transformed by 10 units of force. So that is why this graph now will vary between 0 and 20. Yes, sir. Yes. The 10 that we've added here, it is the difference between saying that you have e sine omega t plus phi. You have one graph like this, and you have another graph y prime is b plus a sine omega t plus phi, where b is a constant. What happens? This just transforms the whole graph up by b. Understood? No, but it doesn't change the amplitude, it doesn't change the frequency. So same thing over here. So hope this is clear, Sudhir. Okay, so let me just summarize and take us back to the problem we were doing and how far we reached. Good. So we saw that, these graphs and all were unnecessary. Okay? Basically, you could just use the direct formula that you can see that the function we are dealing with to begin with in the question was this function. So we are dealing with this function. So straight away we could have seen that y is e sine square ax minus omega t plus something. So we can see from this that the sine square function, it has a fundamental period of pi. So therefore, by formula, what should k become? It should become pi by lambda. And what should omega become? It should become pi by t. And therefore, what should frequency become? It should become omega by pi. Here directly from our theory, we can directly apply this. Okay? The graph was just to show you numerically how this is actually happening. But rest we have directly found out the value of lambda from this only, that lambda was in meters, and you found out from this that the frequency was 40 hertz. So now you also know the wave speed will become f lambda. It will become 320 meters per second. Okay. So that is what this was about. So we saw directly from this, we found out, and the fact that y is varying between 0 and 20. Okay, so amplitude is becoming 10 because extreme to extreme is double of the amplitude. So y maximum y minus y minimum, extreme to extreme is double of the amplitude. So from that you're getting this, from the fact that fundamental period is pi, you're already getting lambda and you're getting this omega. You're getting time period, yes, time period and frequency, all this is done. Now this was just a way to explain why this is the case. So we saw the snapshot, okay, at t equal to 0. So when we do that snapshot diagram, we saw that there is a periodicity of lambda equal to t. So that's why the wavelength is in. And similarly, we saw the oscillation, fix the value of x to 0. We saw the oscillation of a specific particle, and that in this case was a particle at x equal to 0. And we saw that oscillation can be interpreted in two ways, that either you think of it like a sine square oscillation. So again, that sine square function has a fundamental period of pi. So that oscillation 40 pi will actually become pi by time period, or become frequency into pi. Like that. Okay. Or you can further write the sine square function in terms of cos 2 theta and make it this type of function. You can make it a SHN which has a displaced equilibrium position. The equilibrium position is not at x equal to 0, or in this case y equal to 0. The equilibrium position is at y equal to b, which in this case is, again, when you write that function, it is 10, and the amplitude is also 10. So it is 10 plus 10 sine omega t plus phi, where that sine omega t plus phi term is actually this. It is minus cos 80 pi t minus pi by 3. So that is what we understood over here. Okay. Now coming back to this, the final part in this question, you can see that the wave speed, okay, the propagation speed, you can always write it as omega by k, or that is the same thing as f, and that will work out. So omega here was how much? It was 40 pi radians per second, and k was pi by 8 meters per second. So that is the same thing as the frequency that we found, 40 hertz multiplied by the wavelength, which is 8 meters. Okay, so that is 320 meters per second along the positive x direction. This is the propagation speed along positive x axis. So that completes everything in this question. Okay, people, so hope this is completely clear. That sine square or cos square can just be treated as a variation of sine or cos. It's just a variation of a sinusoidal wave. Okay, so people hope this question is fully clear. Just let me know if there's any doubt about any part in this. Okay. Now coming back to more about the general equation. Couple of more things we'll see. Particle velocity question में पूछा नहीं था, but particle velocity अगर निकालना है, then we use that equation. Okay, that particle velocity will become del y by del t at a general point x. Yes, we have to do the partial difference, and particle acceleration will become del 2y by del t square. Now for doing these also, you will see it is easier if you convert that sine square to a single sine. Okay. So instead of sitting and differentiating this, whole thing, what you do is you first reduce it to e by 2, 1 minus cos of 2 omega t minus 2 kx plus 5, and substitute this function. It will be easier to work this because it's easier to differentiate a single cos or sine compared to a sine square. So in case you ask to find out particle velocity and particle acceleration, given a sine square or a cos square kind of function, it's always easier to first reduce it to this using the half angle formula. Okay, now coming back to the general equation, we have y is equal to some function of kx plus or minus omega t, which is twice differentiable. Okay, now in this, one more thing we saw, just now we were talking about particle velocity, del y by del t, that becomes what? It becomes plus or minus of omega f prime of kx plus minus omega t, and particle acceleration del 2y by del t square becomes omega square f double prime kx plus minus omega. Now similarly, if you see, what is the quantity del y by del x? This is the rate of change with respect to x when you kept the time constant. So what is the interpretation of this quantity? It is the slope of the y versus x graph at a fixed value of time. So it is nothing but it is the slope of the tangent at x, at a general point x, in the snapshot picture. That is the meaning of this. So if we made a snapshot picture at some particular time, so we are plotting y versus x for that graph, whatever that graph is, maybe it's something general like this. So at some t equal to t naught, fixed value of time is slope of x. Now, I mean the graph is like this, the snapshot picture. So if at a particular point x, see if at a particular point x, on that graph we draw a tangent, okay, then the slope of this tangent is that. Okay, so that is the significance of this. And that you will see becomes what? That becomes equal to, now just partially differentiate this with respect to k. With respect to x, del y by del x. This will become k f prime. Okay. And similarly, del 2y by del x, that will become how much? Partial differentiation of that one. So that will become k square f of kx plus minus omega. So now you look at this relation here, and you look at the similar kind of relation, second derivative with respect to time, partial derivative, but of time. Look at these two. So comparing these two, you get another important property. you get that del 2y by del x square is equal to k square by omega square times del 2y by del t square. You get this related. And that is nothing but del 2y by del x square is equal to 1 by v square times del 2y by del t square, where v is omega by k is nothing but the propagation velocity. So I'll explain the significance of this differential equation, but just note down this thing also first. First of all, understand the significance of del y by del x. ये क्या होता है? This is the slope of tangent at a general point x equal to x for the snapshot graph, snapshot picture at fixed time t equal to. That is the meaning of this. The slope of tangent thing will have an importance in two things we're discussing later. And similarly, now if you just calculate the second derivative of y with respect to x, the second partial derivative, you see, compare that with the second partial derivative with time, and you see there's an easy relationship between the two. Okay, people, so hope you are clear up to this step here. So you understood this. So where is this equation coming from? It is coming from comparing this one to this above one, this one. Comparing this equation and this equation. Okay, so what is the significance of this equation? Let's understand. This one, del 2 y by del x square is equal to k square by omega square. Del 2 y by del t square. this equation is basically what we call the differential equation. That represents y is equal to f of kx plus minus omega t, where f is continuous and y is differentiable. So we won't get into partial integration over here and all that, but you can show by those kind of steps that this equation actually implies that the function which is satisfying this is of this form. It has to be linear in itself. So it is, somewhat like saying that when we talk about SHM, the relation between displacement and time is this. So this is the displacement versus time. Or we can also write this as d2x by dt square is equal to minus omega square x. This is also the equation of SHM, but in differential equation. So like that, when we talk about 1D transverse wave, we have the general equation where there's a condition on f that it is continuous and twice differentiable. Or we can say that's the same thing as saying that del 2y by del x square is equal to is equal to k square by omega square del 2y by del t square. That's the same thing as this. This is also the equation of the wave, but this is equation of wave in differential form, in differential equation form. Now, generally at our 10+2 level, high school physics level, etc., we don't look at it in this form. So you won't find this equation in Resnick, Halliday, etc. But in some guidebooks for JE, like DC Pandey and all that, you might find the equation of wave is written in differential equation form, which is this. So you can use this equation or this equation, the one below, alternately. This is also the general equation, this is also the general equation, but this is in differential equation form. And this, along with the equation, you have to also write the condition on the function, that it is twice differentiable. Whereas here, anything that satisfies this equation is obviously twice differentiable, because you have used the second derivative itself. Okay, so that is another significance of this. It is actually the type of question we have already seen with that. So for example, I had given you this thing that you have an equation like this: y is equal to, let us say, 1 upon 2x minus 3t whole square. And we have another equation which is, let's say, 1 upon 1 plus 2x minus 3t whole square. Now you can see that both these equations are of this form. Okay, they are of the form kx, the argument of the function is linear extent. But this does not represent a wave successfully. This represents, why? Because this is not continuous and it is not twice differentiable. The derivative will not exist at certain points. So you will see that when you apply this equation here, when you differentiate this twice with respect to x and twice with respect to time, you see this relation holds. but that second derivative does not exist for certain points. Okay, so immediately it will tell you that this one does not successfully represent the wave. This one represents the wave. Okay, so that is the significance. So given any equation, you can check this condition to see whether it's an equation of a wave or not, or you can also directly use this equation to check. If the given equation represents a wave, it will definitely satisfy this differential. You understood the point? Now let's come to, so we saw general of a sinusoidal or what we call a harmonic wave. So that one is represented by E sine kx plus or minus omega t plus some fixed constant. So in this, as we saw last time, the amplitude is equal to E. E is equal to 2 pi by lambda. Omega is equal to 2 pi upon time period or 2 pi into frequency. And of course, we have the relation that propagation speed, which is omega by E. Now, this is only speed, so I'm not putting plus minus sign over here. So I'm just talking about propagation speed. Or we have the relation B is equal to F. Now, this relation becomes very important to understand in another context. So before that, let us look at another way of understanding where the equation comes. So another approach to the equation of harmonic wave. So this is more like an experimental kind of approach. So let's imagine that we have a very long string going to x tending to infinity on that side, and this boundary is x equal to 0. This is a general point x equal to x. So this is a string which has tension P and it has linear mass density. In this chapter, we use the symbol mu for linear mass density instead of lambda, because lambda we already use for the wavelength. But this is in kilogram per meter and tension is obviously in meters. Now what we do is, so this is a very long stretched string. That means it is under tension. And obviously we are assuming it is an isotropic string. So the linear mass density is constant. Now, at x equal to 0, a simple harmonic oscillator given by y equal to E sine omega t plus phi starts disturbing the string at t equal to 0. Okay. So what we do is we just think that we attach an oscillator to the point x equal to 0, which starts forcing the oscillator to go up and down like this according to this equation. Y at x equal to 0 becomes E sine omega t plus, where we understand that omega is equal to 2 pi f, f being the frequency of oscillation of the so-called source of the disturbance, the source being the simple harmonic oscillator. So now what we'll understand is that this disturbance, it starts traveling along the wave, along the string at a constant speed v. So if the point x equal to 0 started oscillating at t equal to 0, when will the point t start oscillating? It will start oscillating after certain delay time. So the oscillation will travel to the point t at t equal to delta t. So what happens is that this disturbance created by the source it starts propagating at some uniform speed v. Why uniform? Because the string is isotropic. So it has isotropic means it has uniform physical properties. So how it carries this elastic energy? Because what is happening is that where you attach the simple harmonic oscillator at x equal to 0, you are creating elastic energy as well as kinetic energy. Because you are forcing the string to stretch and compress as you are forcing that point up and down. And also you have a physical section of the string which is alternately accelerating, decelerating. So you are creating mechanical energy by supplying some power at a constant rate. The source, the simple harmonic oscillator, is supplying a power at a constant rate to make that go up and down. And that power is getting propagated, that energy is getting propagated per unit time along the string. Okay. So if we assume that there's no damping of the energy, that is, there is no dissipative force, what will happen is that that energy will propagate at a uniform rate, that same rate at which the source is providing power. And now more and more particles will start oscillating. And they will all start oscillating with the same amplitude. Okay, so that is the process that is happening. And those oscillations will travel at some uniform rate. Why uniform rate? Because the particle to particle interaction which is happening along the string, that is happening at the same rate between any two particles, because it is isotropic. So that's how we assume that the rate of propagation or the propagation speed v should be constant, because the string is the same, isotropic. So as a result of this, okay, at an arbitrary point or any general point P, which is at x equal to x, okay, the oscillations start after a delay delta t, where that delta t will be basically what? The distance the disturbance is traveled divided by the speed that it is traveled. Okay. So at x equal to 0, the disturbance was given by this equation. So correspondingly, at x equal to x, the disturbance will be given by omega but into t minus delta, because it's got delayed. This process of disturbance has, this one starts at t equal to 0. With the initial phase constant phi. This one starts after a delay. That's why its time parameter is delta t less than this one's time parameter. This is started at delta t. This is started at t equal to 0. So for this, omega t is equal to 0 at t equal to 0. But for this factor of omega t minus delta t is 0 when? At t equal to delta t. Okay. So further, now we substitute. Delta t is how much? It is x by t. So what is the general equation for y at the point x equal to x? It is e sine omega into t minus delta t, which we write as x by v plus whatever phase. So you can see that you're getting the general equation of the wave y as a function of x and time as e sine omega t. Now you can write that omega by v as some new constant t plus some phase. So this becomes where k is nothing but omega by v. So you understand that omega, which is 2 pi f, is the property of the source. It is the source's property. It has nothing to do with the string. It is independent of the medium. It is nothing but the string. But V depends on the medium only. That is, it depends on the string's physical properties. Which ones we'll discuss in a moment. It does not depend on. So V is independent of the source. It only depends on how the string makes energy propagate from one point to another. So it only depends on the physical properties of the string. So what happens is K, which is omega by V. Now K depends on the source as well as the medium. So in this relation, K is equal to omega by V, or that's the same relation as V is equal to F lambda, where F is omega by 2 pi and lambda is 2 pi by K. So we understand in this relation now, F is the source's property. V is the medium's property. But lambda depends on both source and the medium. So this is a very important point to understand. The relationship between the three important parameters of the wave, the propagation speed V, the frequency of oscillation F, and the wavelength lambda. So in that, each term has its own significance. F is exclusively decided by the source. It's controlled by the source. It is independent of the medium. V, on the other hand, is controlled completely by the properties of the medium. It is independent of the source. And therefore, lambda adjusts itself according to the equation V is equal to F lambda. It adjusts itself according to the source's properties and the medium properties. Okay. And also, you are seeing there's an alternate way of deriving the equation of the harmonic wave. Understanding it more from an experimental point of view, that what will happen if I actually carry out this experiment with the assumption that there's no loss of energy, there's no dissipation of energy as the disturbance progresses along the string. So particle to particle, as the disturbance is traveling, the amplitude does not get affected. The amplitude remains the same. So if your particle at x equal to 0 was forced by the source to start oscillating at t equal to 0, the particle at the distance x equal to x will similarly get forced to start its oscillation with same amplitude and same frequency, but with a different phase, because the oscillation would have started at a different time. So you can see there's a phase difference between x equal to 0 and x equal to x. And that phase difference can be calculated in terms of the distance between them, x. Okay. So don't worry, I'm giving you time to write this down. First thing is you understand this whole thing. So you understood this earlier. Okay. Now coming back to general equation, we are going through another approach to understand the equation of the harmonic. So you can just note down the key points here, and of course I will provide you with the notes. So make sure you understand and note down the key points. Yeah, sorry students, I just lost connectivity for a moment. Yeah, so sorry, my internet connection just went out for a moment. So yeah, hopefully I'm back online now. So right, so let me scroll down for you. So this equation is representing the displacement or the disturbance at the starting point of the string or at the end of the string where you're oscillating it forcefully using the source. So that disturbance as it is traveling along the string, you can see that at a general point P, it creates a disturbance which is now given by this equation. So this general point like this, but compare the two and there is a phase difference between them because of that time delay delta t, and that time delay itself is proportional to the distance between them x. Okay. So by understanding that this delta t is actually proportional to x, this equation here, delta t is proportional to x. Yeah, we have to assume the string to be very long because if it has a boundary at some finite position, so what will happen is that as the pulses reach that boundary, they will reflect and come back. Okay. And that will create a superposition effect. So we don't want that. We want the wave to only propagate in one direction. We don't want any reflected wave to come back. That's why we have to assume it to be infinitely long. We will see the effect of this reflection in a different situation now. Okay. If it has a boundary at a finite point and reflected pulses start coming back, it will create what is called standing waves in the string. There will no longer be a progressive wave. It will create standing waves. Okay. So we want to avoid that at this stage. We want the wave to propagate without any reflection. So we have to keep the string infinitely long. Okay, so hope all these points are fully clear now, people. Okay. So this is the alternate way of understanding the general equation of the harmonic wave, and it clearly shows the relationship between the frequency, wavelength, and the wave speed. Okay. How the frequency is nothing but the frequency of the source which is a simple harmonic oscillator. Whereas the wave speed we will see next, it depends on the medium properties. So let us now understand the propagation speed. V. So we will understand this in this way, that suppose there is a pulse that is traveling along a string which has tension P and linear mass density mu, so not lambda, but here we use the symbol mu for it. Now imagine an observer who's traveling along with the pulse. So this is an observer in the frame of a pulse, okay, or it could be the crest of a periodic wave. Now imagine that observer as he's traveling in that frame, he is making the FBD of a small section of mass dm. So the free body diagram of a section dm at the crest or peak of a pulse in the given observer's reference frame. So what that observer sees is something very interesting. He sees that particle dm with respect to that observer who's traveling with the crest. He sees that particle to have a velocity along the negative x direction, and he sees it to have an acceleration in the downward direction. So how do we know this is what is happening? Because in the ground frame, okay, the particle dm at the peak or crest is at rest. Why? Because del y by del t will be 0 at y equal to y max. So particle velocity will be 0. Okay. But it's going to come down next. So it should have a downward acceleration. So therefore, in his frame, what is happening? Remember that after all, he is traveling with a uniform velocity, so he is an inertial frame. So he'll see the same acceleration as is seen in the ground frame, but he will see the velocity to be backwards. Okay. So therefore, in the observer's frame, that acceleration is v square by r, where r is some instantaneous radius of curvature. Of that particle dm's trajectory. Okay. That particle is actually coming straight down, but since that observer is moving along the horizontal direction with a uniform velocity v, तो उसके frame में particle का trajectory कैसा होगा? With respect to this observer, okay, who's traveling like this, that particle is at rest at the moment. I mean, it's in the ground frame, it's at rest, but it's coming down. So in his frame, it will have a trajectory like this. So it has a curvilinear trajectory. Okay. So as it has a curvilinear trajectory, it has some instantaneous radius of curvature. So because the acceleration is purely centripetal or it's purely normal, So it should be equal to v square by r. So now based on this, he will make the free body diagram and understand that what is happening is that now if he understands the particle as a section of the string, so again in this observer's frame, who is of course an inertial observer, that section of the string dm is subtending some small angle d theta at the center of its instantaneous radius of curvature. That one. Okay, so r is the instantaneous radius of curvature of that particle dm's motion. Okay. So the forces acting on this are tension and tension like this tangentially, where you can see that if we draw these axes, then these two angles will be the same as this half angle. And that particle is having a downward acceleration or a centripetal acceleration of t. So the FBD equation here, just applying simple mechanics. Okay. So the net centripetal component of tension, that is 2t sine d theta by 2, that is what should be providing the particle dm with its acceleration, which is nothing but v square upon instantaneous radius. Okay. Now here dm should be equal to mu into the arc length, where this arc length ds is nothing but r d theta. So further this equation becomes 2t sine d theta by 2 is equal to mu r d theta, that's the mass dm, into v square by r. Okay. And sine d theta by 2 will be approximated as d theta by 2, it will be the small angle. So 2t into d theta by 2 become approximately equal to mu r d theta into v square by r. So you can see that that will give you the simple relation between the speed, okay, the tension and r, or v will be equal to, sorry, speed, tension and mu, r will cancel out. So for example, if tension is, let us say, 1000 newtons, okay, and linear mass density is, let us say, 0.4 kg per meter. So you see that the speed of this thing will become like this. Speed of a transverse wave on that will become 50 meters per second. 100 by 2. This is a typical kind of example. So, but more importantly, this formula. So you can see that the speed of propagation only depends on the medium's properties. And which properties of the medium? For a transverse wave, it depends on the tension or the tensile force along the length of the string and the linear mass density. Okay. So I'll just leave you to quickly note down the key points here again. Okay, so hope this part is clear. All right, so this is the complete derivation of the speed of a transverse wave, how it depends on the tension and the linear mass density. And as expressed before, it is completely dependent on the medium properties. So we can also express this relation V is equal to F lambda now as square root P by mu is equal to frequency into lambda, or lambda is equal to 1 by F square root P by mu. So that is how you can see lambda depends on both the properties of the source, that is the frequency of the source, which is a simple harmonic oscillator or whatever, and the medium, that is the string's tension and linear mass density. So this depends on both these things, source and medium. So it's like a self-adjusting quantity, which depends on both of these. Okay, now next property of the harmonic wave we'll see is the power transmitted through the wave, or the power supplied by the source. To a harmonic transverse wave, specifically, not the general equation, but the sinusoidal kind of that one. So again, if we consider a sine wave propagating like this, let's say after some time, as it's propagating, it's something like this. So you can see that any medium particle, dm, it is undergoing an oscillation up and down like this. So the mechanical energy of oscillation for a particle of mass dm on the string, it is such that its kinetic energy, instantaneous kinetic energy, is half dm into particle velocity square. So that is half dm into del y by del t square. Now we are talking about a harmonic wave, so obviously our y as a function of time is this general equation. So the instantaneous particle velocity, kinetic energy becomes half dm into e square omega square cos square omega t plus minus kx plus 1. Okay. So we can see that average kinetic energy. So this is basically what this is, the instantaneous kinetic energy, okay, of the particle dm at time t. So the average kinetic energy, the time average of kinetic energy, that we can write as this thing, because this is the only thing that is varying with time. So this is the average of the cos square function. Okay, now we'll do a separate derivation and I'll show you that cos square omega t plus or minus kx plus phi averaged out, averaged over time, has a value of half. So therefore the average kinetic energy of oscillation will become 1 by 4 dm into omega square into e square. Okay. Now since these particles are in SHM, we will say that the average kinetic energy just a minute, Shruti, you're asking since omega t had a plus minus, then why it has in this? That's the same thing. Okay, let me explain one thing. Okay. See, Shruti, whether we write the general equation as sine kx minus omega t, this is the same thing as sine omega t minus kx, but with some different phase constant. Okay, because sine theta is minus of sine this, okay, which can be written as okay. So for example, sine of kx minus omega t can always be written as sine of omega t minus kx plus phi. Understanding? So it doesn't really matter whether we write kx minus omega t or omega t minus kx. It's one and the same. Okay. So that's why. So if you compare this and this here, phi prime is just phi plus phi. Okay, Suti, this is it clear why they are interchangeable. Okay, we write the general equation as E sine kx minus omega t plus phi. It can also be written as omega t minus kx plus some different constant here. Okay. And similarly, if there's a plus sign here, there's no problem at all. Here also will be plus sign. Okay. So it's just a matter of phase, whether we write it as omega t plus minus kx or kx plus minus omega t, it's one and the same thing. The important thing is it has to be linear in x and t. Okay. So coming back here, we are seeing that and a particle of mass dm, its average kinetic energy during the oscillation is this term, 1 by 4 this. So since they are in SHM, okay, the average kinetic energy will be the same as the average potential energy, which is elastic potential energy of the string, which will be 1 by 4 dm omega square e square. So we can say that the average mechanical energy of oscillation for that particle d, that is sum of average elastic potential energy plus average kinetic energy. So that becomes 1 by 2 dm omega square t square. Okay. Or we can write that average mechanical energy of oscillation as half mu dx into omega square t square, where dx is the length of that section which has mass d. Therefore, power transmitted will become the rate of that average energy per second. So that will become half mu dx by dt. Now dx by dt, or dx is nothing but v dt, where v is that square root of this place. Okay. So that's how the power is becoming half mu v omega square t square, or more precisely, you can write it as square root of t mu into omega square t square. Because remember that v is equal to square root of t by mu. So that cos square function's average value is half. That I will show you by integration again. But you can understand that whatever that average value, the proportionality will be like this only. Okay? So just make a note of this section. It's not something as simple as a single particle in SHM. There is certain amount of what we call delocalization of energy. But as far as the average energy per particle is concerned, it's that much only. The average kinetic energy is this much, the average potential energy is this much, so the average mechanical energy of oscillation over time will be that much. So that average energy, how it is propagating with respect to time, or its rate of change with respect to time, that becomes the power transmitted. Okay, so just go through the derivation up to here, then we'll come back to the average value of cos function, or rather cos square function. Okay, so we'll come back to the formula of power, but first let's understand this average value of cos square function and its significance and all that. So let's concentrate on this section over here, the instantaneous kinetic energy of that particle. So let's try to understand why we have averaged out the cos square function and how we've averaged out and all that. So let's understand. The instantaneous kinetic energy of that particle is half dm into omega square e square cos square of omega t plus some constant, I can say, okay, because we are talking about a particle, so that omega t plus or minus kx plus phi, this thing for that particle is a fixed quantity. For a specific particle, so x is some x naught, x, okay. So that kx naught, that plus or minus kx naught plus phi is a constant with respect to time. Okay, so we can write this like this. Okay. So that is the instantaneous kinetic energy. So that instantaneous kinetic energy you can see as a function of time, it is varying. It's a cos square function. So it's varying like this. It's not constant. So its average value क्या हो जाएगा? The average kinetic energy, that will become, how do we calculate average in calculus? By calculating the area and then dividing by time, because this is kinetic energy versus time graph. So this is the area under the kinetic energy versus time graph divided by the time. This kind of thing. That's how we calculate the average. So that will become over here integration of this thing over time, okay, divided by time. Now this is for a periodic function. So for a periodic function, we can always calculate this area over this kind of time and divided it by one cycle. Because over a large time, the time average will be the same as the average over one cycle. So that's how we'll prove that cos square function, the average value becomes half. Okay. So just a second. I'll be back. So this is what we want to calculate over here, the time average of the kinetic energy of that particular particle. So when we calculate this thing, see that this time average of kinetic energy, it is basically half dm omega square e square cos square omega t plus alpha, okay, integrated over time divided by time. This is the quantity. So because that cos square function is a periodic function, so we can just do this over one cycle. And divided by that cycle. So this thing is nothing but half dm omega square e square into what we call average value of cos square. इसको ही हम शॉर्ट में क्या लिख सकते हैं, cos square function का average. Where that average value of that cos square function is nothing but integration of cos square over one cycle And because of the symmetry of this, you can understand that it has the same average value independent of this constant alpha. So further I can equate this with what? I can equate this with cos square omega t dt's average over time. This alpha will make no difference to the average value because the shape of the graph remains the same. It's just transformed. So I can just remove the alpha or take the particular case of alpha equal to 0 because the answer should be independent of alpha. So alpha ka value mein 0 bhi to same value मिलेगा. Now this is something we can easily do. So we can see that this quantity is becoming cos square will be written as 1 plus cos 2 omega t, the whole thing divided by 2, 0 to t divided by t. So this thing further will become 1 by 2t into t plus sine 2 omega t, okay, by 2 omega integrated from t equal to 0 to t equal to capital T, which is by the way 2 pi by omega. So you can see that when we put these limits, we get 1 by 2t into t minus 0 for the first term, and we get sine 4 pi minus sine 0 divided by 2 omega for the first term. So we get half. So this is something which is quite important in physics actually. Just from this point onwards, you should remember this, that the average value of cos square function, time average value of cos square function becomes like this. Okay. So I'll leave you time to note this down and all that, but let's come back to our derivation here. So how we use this over here is that from the instantaneous value of kinetic energy, we are coming to the average value of this one. So this, what we understand is that cos square omega t plus phi, let's say, has the same average value as cos square omega t, which has the same average value, in fact, as sine square omega t, because they are the same kind of graph. Okay, they're just transformed. They're just having a phase difference, which is equal to half by integration method. So in physics, whether we are dealing with a sine square function or a cos square function of time, integrated over, over a large amount of time, its average value is the same as its average value in one cycle, and that average value always comes out to be half. Okay. So that's how this factor being half now, this whole thing now becomes half. So that's how we get this factor of 1 by 4. So that's how we are getting the average kinetic energy equal to the average potential energy by that symmetry is 1 by 4 dm omega square square. So the average mechanical energy during that oscillation per cycle, the average mechanical energy is so much. So the power becomes the rate of that energy propagating per unit time. So it becomes this, and that's how we proceed further. So I'll just leave you with a bit of time to absorb this, but this is a standard application of integration, which you would have studied in maths also at some stage. The average value of a function using integration. Okay, so just the last few steps of this integration. Okay, so I'll explain the integration part again. So the integration part is like this. कि हम क्या कर रहे हैं? Cos square omega t का average निकाल रहे हैं. So we are integrating this and dividing it by time, but over one cycle. Okay. So in the original SHM wave or harmonic wave, that cyclic time is 2 pi by. So t is equal to 2 pi by omega. So this is the cos square function's average value. So now we can write cos square theta as 1 plus cos 2 theta by 2. So doing that, this is 1 plus cos 2 omega 2 by 2 integrated from 0 to t divided by, so take the 1 by 2 outside and the t from the denominator. So it becomes from 0 to capital T, which is, by the way, how much? It is 2 pi by omega. So substitute this now. So integration of 1 dt is t, and integration of cos is sine, but it is cos 2 omega t. So it becomes sine 2 omega t divided by the coefficient of t, which is 2 omega. And on this, we'll put the limits from t equal to 0 to t equal to capital T. Okay. So this will further, on putting the limits, become upper limit minus lower limit. This will become upper limit minus lower limit. So this will become t plus, now sine 2 omega capital T will be sine 4 pi minus 0 divided by. which is also 0. So that's why this becomes half. So that's how this cos square omega t function's average becomes. Okay, so hope this integration part is now clear, Sudhi. Yeah, that is the whole point. You have to remember this for future applications. The average value of cos square function is equal to the average value of sine square function is equal to half. This comes in a number of places in physics, including things like alternating circuits and all that later. So you see that this is a useful result to remember. This result here is something useful to remember. That the average value of the cos square function or the sine square function is always half. So now having done this average value thing, next thing you understand the power. So basically what is happening is that as the wave is propagating, let's say the wave is over a distance x at a time t. So what will happen, because it is propagating at a speed v, the extent of the string which is oscillating will have changed to x plus dx in a time t plus d. So in that time, this time, how much extra energy has come? So that is equal to that. So the power transmitted by the source is that extra energy which has come in that time. So that is half mu v omega square. So that extra energy is half mu dx. So every time dt, another particle of length dx is joining the wave motion. So the total energy of the oscillating particles is increasing by an average value of this much in a time dt. So ये जो average mechanical energy है वो किसका energy है? वो एक section of the string dx का energy है. So between a time t and a time t plus dt, the section of the string which is oscillating is increasing in length from x to x plus dx. So in that time dt, how much extra energy has come? The extra energy which has come is that dt. So the power is the rate at which that energy is being supplied by the source. So that's why it's dE by dt, and that's how it becomes this. So Sudhir, while you can memorize this cos square function's average value is half, and you should know it that its value is half, but you have to also understand where it comes from, why its value is half, and that understanding comes from the integration. So the steps of the integration should be clear to you. So the formula of this average power thing is clear now. The power transmitted through the wave, which is also the power supplied by the source. So that's the idea. So for example, if we have a situation like this, that you have a string which is having a tension, let's say of 250 newtons, like the tension due to a 25 kg mass hung on the string, and it has a linear mass density of, let us say, 4 gram per centimeters. Now find the power propagated to a wave, or the power supplied by the source for a sinusoidal transverse wave of amplitude equal to, let's say, 2 millimeters and frequency equal to, let's say, 20 hertz propagating through the string. So how much power will such a source have to supply in order to keep that wave propagating? Because as the wave propagates, the total number of particles in the string which is oscillating is continuously increasing. Like we discussed in the derivation of that harmonic wave today. What's happening? That disturbance is traveling at a speed v. So it is continuously involving more and more particles into oscillation. So while the average energy of oscillation of each particle is fixed, but the number of particles that are involved in oscillation, that is continuously increasing. So you are creating that disturbance to the source over here. After some time, these many particles are oscillating. After some time, more particles are oscillating. So as this wave is propagating, more and more particles are coming within the extent of the wave. So the total energy of oscillation of the system is continuously increasing, and that is nothing but the average power which is propagated. Okay. So now this becomes a formula based question. So you can see that tension was 250 newtons, linear mass density was 4 gram per centimeter, which can also be written as 0.4 kg per meter, because gram per centimeter would be 10 raised to minus 3 upon 10 raised to minus 2. So that's 10 raised to minus 1 kg per meter. So 1 gram per centimeter is converted into 0.1 kg per meter. Keeping that in mind. So now the power transmitted will just come by this formula: half square root of P mu omega square E square, or half mu V omega square E square, where the speed of propagation is square root of P. So it's just a simple calculation like this, nothing extraordinary. So just half square root of 250 into 0.1 into omega is 2 pi into 20 into was, I think, 2 millimeters was the amplitude or whatever. So convert that to meters because we want the power in watts or joule per second. So this power that we will get will be in watts or joule per second. So that's it. That's all there is to this. And you can take pi square as approximately 10. So it becomes the even easier calculation. So I think this will become 10 into 10, 100 into 100. Okay, so 4 into 10 raised to minus 2 watts, or 40 milliwatts. Oh, sorry. Minus 16. 4 pi square into 400, that's fine. Into 4 into 10 raised to the minus 6. Oh, linear mass density is 0.4 minus. So I have to this one. So there's another factor of 2. So this will finally become how much? 16 by 2. Is it correct now? Just check. Yeah. No, still not correct. This is 64 by 2 into 10 base power. I'm taking pi square as 10 as well. Minus 6 plus 1. 32 to 10 raised by minus 2. 0.32. Anyway, whatever the value is, the method clear. Oh. So anyway, that's just that relation. Now, one thing which is more important here, which is a property of wave that many people actually don't understand properly also, is that the concept of energy. Now, energy propagation happens. Just give me a minute, people. I'll have to shut down the whiteboard and restart it. Just give me a minute. So coming back to this point, which I want you to understand in detail, energy propagation occurs to a wave or takes place in a transverse wave such that energy is continuously delocalizing or it is continuously shifting. It doesn't remain fixed at a certain point. Okay, so it's continuously shifting such that any section dm of the medium, in this case a string, keeps gaining and losing mechanical energy. It keeps going from maximum to zero alternately. That's why we have talked about the average energy. So I'll explain why that happens. Unlike an SHM, in an SHM the system's energy remains constant. But here if you look at a particle on the string, as it is oscillating up and down, interestingly its energy is not remaining constant. Alternately its energy is becoming maximum and then again is losing that energy, then again is becoming maximum, then again is losing that energy. So let's understand why that happens. Okay. So if you look at t equal to t1, you look at the snapshot of the wave y equal to e sine omega t plus or minus kx. That's fine. In fact, let's take this case where it's propagating in the positive direction. The demonstration, so this is minus, okay, and this is at some t equal to t1. So let's say the snapshot picture at this moment of time let's say is represented by this. So this is at some time t1. Now, a very short time later, it would have become like this. So this is at t equal to t1 plus some short time delta t. Whereas if I see exactly 1/4 of a time period later, it would have become like this. The crests and troughs would have got alternated. It would have become something like this. This is, let's say, at t equal to t1 plus quarter of a time period. You can see that the particle which was initially at extreme has now come back to mean position and vice versa. Okay. Now, in this, if you just observe the difference between a section of the string which is at t1 over here. This is section, let's say, A of the string, and this over here is section B of the string. Okay. So at t equal to t1, a section tm of the string at the point P, or let's say this point is A1, so that we don't confuse it with amplitude. At the point A1, what can we see about that section? So if I draw more this thing detailed diagram of that section, so what I can observe about the section of the string which is at that point which I had labeled as E1. So I'm talking about this section. ये जो DM है, तो यहाँ A1 वाले point पे. Now what is happening to this section is that as the wave is propagating like this, you can see that this section is going up and is going up with maximum particle velocity of d omega. Okay. So that section dm has kinetic energy equal to half dm omega square t square, which is maximum kinetic energy. Okay. Now the other thing you can see is also the potential energy of that section is half into stress into strain into volume, which is whatever area into dx. This is also maximum. Now, why this is maximum? Let's understand. Okay. So, what is happening is, suppose this is the natural shape of the string. This is the natural shape of the string. Now, from this, if we stretch it to a position like this, in this position, the string is stressed. Now, as it is stressed, you will see that जो section यहाँ पे DL का था, वो section यहाँ पहुँच गया, and it is still DL. Okay. So this is hardly stressed. So that section's potential energy is tending to zero. Whereas जो section यहाँ पे था, suppose dx length का, that section now has got like this. It has become like something which has become root of dx square plus dy square. Okay. So what is happening is, so what we can understand is that this section dl at extreme position of oscillation, that is either y equal to plus or minus of t, okay, is not, it is not in a strained condition. It's not in a strained condition. Its natural length, which was dx, when the string was just at its natural position, is still equal to that dx of d at the extreme position. ये भी dx ही है और ये natural position में भी dx ही है. But a section at the mean position, that is y equal to 0 of oscillation, has maximum strain because it is stretched from dl equal to dx to, let's say, dl prime, which is square root of dx plus square plus dy square. Okay. So what is happening to this section is, ये जो ऐसा था dx length का, अब in the strained position, suppose like this, that section has got stretched to this, where that dl prime is the root of dx square plus dy square. So that dl prime is maximum at the particles near the mean position. You can also think of it like this, that if you just take a rubber band, okay, and when it's in this kind of position, you just make some vertical ink marks on it, which are equidistant. Okay. Now you stretch out the rubber band like this. So the moment you stretch out the rubber band like this, you will see जो ink bands यहाँ पे हैं, वो more or less same distance पे रहेंगे, but जो ink bands यहाँ पे हैं, वो बहुत stretch होंगे. Again यहाँ पे जो ink bands है, वो more or less same stretch पे रहेंगे, but जो यहाँ पे पहुँच गया, This is highly stretched out. So you can see that this is under strain. This is under strain. But this is unstressed. This is hardly having any stress and strain. So that means that this section is having high amount of potential energy. This section is having high amount of elastic potential. This section is having potential energy tending to zero. Okay. So this is a very important thing to understand. So I'll just minimize this and take you through this whole section. So ultimately through this what we are understanding is as the wave is propagating, जो ये वाला section है A1 है उसके पास potential energy भी maximum और kinetic energy भी maximum. So therefore the section DM at the position A1 where it was at mean position, okay, y equal to 0, it has maximum energy. And we'll also see next that the section near that point B, which I've taken at the extreme position at that time, that is neither having kinetic energy nor having potential energy. So different particles on the string are having different kinds of energy. Okay, some are having large amount of potential and kinetic because they are near about their mean position, or the ones which are exactly at the mean positions. At those locations in the string, both the kinetic energy and potential energy both are maximum. Whereas some are near the extreme positions or exactly at the extreme positions. So those particles are neither having kinetic energy nor having potential. So as the wave progresses, this mechanical energy keeps shifting from point to point. And accordingly, as each section of the string goes from mean position towards extreme position, it starts losing all of its energy. And as it comes back from the extreme position to the mean position, it starts gaining all the energy back, both the potential and kinetic. So this is what we call delocalization or constant shifting of energy from particle to particle in a transverse way. Okay. So I'll just give you a bit of time to note down this point over here and then come back to the explanation of that point which I've labeled as A1 over here at time t. The point A1 is at the mean position. The particles at A1 are at the mean position at the instant T1. Okay, they won't always remain at the mean position, but at that instant they are going through the mean position. The particles of the string which are at A1. So we will see below that they have both maximum kinetic energy and maximum potential. Okay. So coming back to these particles which are right now at the position A1, you can see that they are having maximum speed also, and they are going to have maximum potential energy. So this potential energy is coming from that formula, that elastic potential energy. How we calculate that? The energy density is half stress into strain. Okay. Or that can be written as half stress square upon Young's modulus, or half into strain square into Young's modulus, whatever, that kind of thing. So therefore the energy is nothing but half into stress into strain into volume of that section. Like that. But we won't be doing an exact calculation of it. This is just conceptual. यहाँ पे stress ज़्यादा है, stress and strain जहाँ पे ज़्यादा है, वहाँ पे potential energy ज़्यादा है. Whereas where the stress and strain is tending to zero, the potential energy is tending to zero. So that concept is illustrated here. That why the point at the mean positions, the particles at the mean position are having maximum stress and strain, because that string over there had got stretched to a hypotenuse, like root of dx square plus dy square, from its natural length of dx. Whereas a section of the string which is here, which has gone to the mean position, is hardly stretched. Its length is remaining dx. Alright, so we've understood the point. We can go through this once more later. So finally, what we realize is that when you're looking at, this is the snapshot picture at t equal to t1. So the particles which are around this point and the particles which are around this point, particles at d1, they have zero kinetic energy, zero potential energy, because they are at extreme position. Whereas particles at E1, they are having maximum kinetic energy, they are having maximum potential energy. So they are having maximum mechanical energy. They are having minimum mechanical energy, in fact tending to zero. Now, by the time the wave shifts one full quarter cycle, so at T1 plus T by 4, ये पूरा pattern ऐसा shift कर लिया. So it would have become like this. So these particles by now have shifted here, and these particles have shifted here. And similarly, the particles which were here, let's say this, these particles have gone. So now you can see at t equal to t1 plus t by 4. This was all happening at t equal to t1. Now at this new time, particles at a1 have zero mechanical energy or minimum mechanical energy, and b1 has maximum. So what is happening, that is how we understand that as the wave is propagating from this to this, the energy of these particles, they all go here. The energy of these particles, they all go here. The energy of these particles, they all go to this section. So the energy is constantly shifting. So every t by 4 time interval, particles going from mean to extreme lose their kinetic energy. I mean, lose their energy. And those going from extreme to mean gain energy. So this keeps happening. So this process is called the continuous propagation, or there's a continuous delocalization. Energy doesn't remain localized, it keeps shifting. So there's a continuous delocalization or shifting of oscillation energy in continuous loops. So that is happening at the rate of power equal to half square root p mu omega squared. Okay. Or you want to see how that energy is propagating in terms of energy propagating through distance with respect to time, that is the wave speed. Okay. So this is an important conceptual thing to understand, and it will become important in standing waves and all later also. So you should understand that in a wave, at a given point of time, the energy is not equally distributed in all the particles. So if the waves snapshot picture right now is like this, and you can see that the particles which are over, let's say at T1, are having minimum energy. The particles right now at T2 are having maximum energy. The particles at a point T3 like this, so the energy at T1 is minimum. The mechanical energy at particles P2 is maximum. The energy at positions like P3 is less than the maximum, but greater than the minimum. So this kind of thing, for conceptual questions like this, you to understand this. Okay. So for example, in Resnick-Halliday, this is explained to a certain extent in detail, but in many other books, including H.C. Verma and all, they don't get so much into the delocalization of energy. They just express the power as the average energy, differentiated with respect to time or shifting per unit time like this. But conceptually, you should understand this concept of delocalization. Okay. So this is where we will conclude today's lecture. And I have sent you some PDF theory notes as well as some questions. So I will send you a list of questions that you can work out, and also from HCV, including questions which have to do with the calculation of propagation speed. And in certain cases, what might happen is that tension in a string might be variable, like you have a heavy rope hanging under its own weight vertically. So the tension is variable. So the tension is variable. You send a pulse along that string, the speed will not be constant. The speed will vary according to how tension is varying. So then you have to use integration to calculate the distance covered as a function of time, because the speed of propagation is variable. So things like that also will come in. And of course, calculation of power and relationship between frequency, wavelength, and power. So quite a significant number of questions we'll be now working on. But you have this test coming up in between. So right now we concentrate on that, and Sunday onwards, when your test is over, you can come back to waves, and I'll send you a list of questions that you can work out. So in the meantime, please make sure that you revise your geometrical optics and practice some questions properly. If there are any doubts in that, please let me know. So that's it for today's class. Thank you.